Hello, everyone. So, today we are going to have a complete insight on atomic operations in C. So, without wasting time, let us start. What is an atomic operation? An operation that cannot be observed partially by any other thread, but lock free, thread safe operations. So, by this, we mean that whenever we are dealing with multi threaded environment, there we have to ensure that the data is not partially observed. Otherwise, any of the threads can might get redundant or irrelevant data. So atomic operations allows us to deal with this problem without using mutex or any locking functionality. So we can see a simple code on the screen. Since code is very short, so we'll prefer to go through the notes itself. So we can create an atomic variable of type int like this. We can use atomic library, and as a template we can pass int, then the name of the atomic variable, and inside the braces we need to pass the initial value. Now if we want to increment, then we have fetch underscore add, which fetches the data, then adds 1 to it. We could have also used increment operator, which is plus plus, and there are many other operators that are provided by the atomic operations as well. We'll see this in the video further. So what are the basic atomic variables that we can create? So we can use int, boolean, long, a void pointer as well. Apart from this, we can also use it on user defined data type as well. But the user defined data type T, let us say, it must be trivially copyable. By trivially copyable, we mean that it should not have any user defined copy or move constructor. It should not have user defined destructor, no virtual functions, and can be copied bit by bit using memcopy. So this is an important note that we can use a template for atomic only if it is trivially copyable, and it has to follow these rules to ensure that it is trivially copyable. So let us take some example that what are the data types that we can use. Int, double, nm, all of these are primitive data types that we can use. Whereas we can use user defined structure as well, like this. But the point to be noted here is we cannot use a struct A which has a string. Why not? Because it is not trivially copyable. Because string is defined in heap memory. It is dynamically allocated the memory, and we cannot copy it using mem copy. So it cannot be copied bit by bit. So these are certain points that we should remember. Now, let us go to the code and take an example how we can deal with this. And let us see what are the differences while using the user defined data type and primitive data type. So we'll create a file and we'll name it atomic.cpp. Now let us try to use a user defined structure as an atomic variable. Hash include iostream. We have to also include atomic. Now let us create a structure, struct point, and inside struct point, I will be using an int x and an int y. Now inside int main, we'll create, before creating, let us using namespace std. Here we are going to say atomic. We will create an atomic int a, which will be initialized with 0. Then we'll also be using atomic of type point structure p. And then I would like to see out atomic int variable that we have created, whether it is lock free or not. So we have something called as is lock free inside the atomic. So we can use the function is lock free and in the same way I will also see out point variable that I have created, whether it is lock free or not. So p dot is lock free and so let us try to compile this now. So it compiled successfully. If I'll try to execute it, we can see atomic int and atomic point both giving an output of 1. So it means both are lock free. The point here that I wanted to show is that it is not necessary that the structure would have been lock free. The CPU can allocate and it can manage memory till 2, 4, 8, and 16 bits. Here we have 8 bit of data, and if we go to the node, it fits into the size, the 8 bit of structure, but still the CPU must support atomic compare and swap on that size, and many platforms will not support this. So the compiler may implement it like taking the lock on for the mutex first and then copy it, then unlock it. So in that case, it will not be lock free. So this is what I wanted to show from the example. In my system, it is lock free, but it may be not lock free on your system. So we have different kinds of functionalities which are provided in atomic operations. These functionalities are first of all load, which is to read the data. We have store to write the data. Increment, decrement is there to increase or decrease the data, but it is only there for integer value. Then we have fetch and add. Again, this is only there for integer value. Then we have compare and swap. Compare and swap function, what it does is it takes two arguments which is expected and desired. If the value of the atomic variable is equivalent to the expected value, then it will set it to the desired one. If it is not equals to the expected value, then it will change your expected value to the current value. And we have two kinds of compare and swap. One is compare exchange strong and the other is compare exchange weak. There's a slight difference in both of them. We'll see that in the video further. So we have only the load, store, exchange, and compare exchange. We do not have fetch and increment for non-integer value. Now let us move on to the compare exchange weak. So like I said, we have a compare exchange weak and compare exchange strong. Both the signatures look similar. They both take an expected value, a desired value. So let us say if the expected value is 5 and we call compare exchange weak, we pass the expected value and the desired value is passed as 10. So in that case, it may return you false as well. Even if the value of x was 5 and we tried to check it, it was equal, but still it returned false. This is not a bug. This is observed with compare exchange weak because we use weak hardware instructions for this. And due to optimization, we can get a false value. So instead of calling the function straight over and getting a Boolean output, what we do is we put it inside a while condition. In case it returns false, then we try to check it again. So eventually it succeeds. This is called canonical lock-free pattern. But this problem is not observed in the compare exchange strong. We do not require a loop. we can write it down inside an if condition, and if it succeeds, we can perform certain operations. But it is slightly more expensive compared to compare exchange weak. Why it is more expensive? Because some CPUs only provide weak CS. In those cases, the compiler has to retry internally, and it has to insert fences and extra checks has to be added. Due to that, the compare exchange strong becomes more expensive than the compare exchange fee, which maps directly to the hardware. Now let us see the memory orders as well. So we have different kinds of memory orders. So how does a memory order use in the code? Let us see that first. So if I have an atomic variable a, so what I can call here is a dot store, and I can pass a value that I want to store. Let us say it is 1. And beside this, I can also pass the memory order. So I can pass here memory order relaxed in this way. Or I could also have passed memory order acquire, release, or sequential consistency. Now let us see all of these in depth and the differences between them. So the first thing is the memory order relax. It provides atomicity only. It does not provide any ordering, no synchronization between threads. By this, what I mean is, let us say we have written this kind of statement. So whenever we use mutex, we lock at some point, then we do some operation, and then we unlock. So whatever comes in between, we have to take care of the visibility and ordering. So compiler can reorder instructions as well as CPU can reorder instructions also. Another thread can see partial or stale data, so it can cause some issues. So when we use memory order relax, it does not provide any ordering or synchronization with the threads. It only provides atomicity, and we should never use it with the locks. The next one is memory order acquire. It says nothing after me can move before me, which is used when acquiring a lock. So it ensures visibility of prior writes from releasing threads. So if we use memory order acquire in the test and set, it means all reads and write operations will be performed after the acquire operation, and it cannot be reordered before it. So when you call the order acquire, whatever comes after it, it cannot be reordered before it. It has to be after this statement only. The next one is the memory order release. It says nothing before me can move after me. So it's similar to the memory order acquire, but the point here is we can use it when releasing a lock and publishes write to other threads. So whatever comes before the release order cannot be reordered after the statement. So we can use log.clear and then we can pass memory order release. Then we have memory order acquire release, which is acquire plus release. It is used when read and write both operations are required. Let us say we want to fetch and add. In that case, we are reading the data as well as we are writing the data. So we can pass the order acquire and release. And the last one, which is the strongest one, is the sequential consistency. It is the strongest order. It provides the global total order of all sequential consistency atomicity, but it is the slowest. So if we write straight away this without any memory order, then by default it goes to sequential consistency, and it is slowest among all of them. And it ensures that each atomic operation is still atomic and no reordering will happen, whereas strong synchronization across threads will be there. So in sequential consistency, all the threads agree on the same order of atomic operations, and no thread can disagree with that. Due to this, we have a sequential consistency. It means that if I have a statement x dot store as 1, and after this, if I have a statement y dot store equals to 1, then no thread can get the value of y as 1 before seeing x equivalent to 1. So the sequence of the operation cannot be reordered for any of the thread, and it will remain consistent for all the threads. So that is all about the memory order and atomic operations. I hope you would have understood a lot. We will also see examples like creating a spin lock using the atomic operations in a separate video. And we will also see how we can make use of it in different design questions. Thank you.